we have been discussing about the different scaling laws which are involved for designing a micro robot. In fact, this module will give us a clarity about what are the different parameters which caters or which governs in actuating a micro robot or for developing a micro robot for different applications. So we had discussed in detail about the different parameters which are involved, like different domains which are involved, and we also had a detailed discussion about the different parameters which has an influence towards the domain. Now, among the different domain, heat transfer is also considered to be one of the key parameters for a micro robotic system. So when we try to consider a micro robot, like one is with reference to power perspective point of view, power and the loading. So when we try to power up the system and when we have an appropriate loading to the system, so there is going to be a certain amount of energy dissipation which is in the form of a heat. So management of the same is one of the key challenge. Then another one is like we have seen in the earlier domain about the drag force which is getting generated when a micro robot is moving in a fluid domain. So this drag force will also have an impact towards the power dissipation. Okay. Now, like with reference to this heat transfer perspective point of view, when we are trying to design a micro robotic system, there are different modes of heat transfer also comes into the picture. So we will discuss in detail. Now, before going into this, let us discuss why we need to have a heat transfer scaling which has a direct impact in the micro robotic system. One is a kind of a miniaturization challenges. So if we look into the miniaturization challenge, so the heat dissipation is harder at small scales due to the reduced conduction and convection. When we look into the thermal management in micro robots are concerned, so this material with high thermal conductivity are required to prevent overheating. And second, it has a kind of a active cooling method. For example, microfluidic cooling or a radiation based cooling are essential. Energy efficiency perspective point of view, these micro robots must balance the power consumption and heat dissipation to avoid the thermal damages. A biomedical perspective point of view, these biomedical micro robots, these heat can damage a biological tissue, and a proper thermal control is essential for this particular system. So in that aspect, so these are some of the key challenges which needs to be addressed with reference to thermal management perspective point of view. Now, in order to understand the thermal management, let us take an example of this application of this heat transfer in micro robotic system. One of the key aspect is the kind of a thermoelectric generators, like we had discussed about this electrostatic charge. The case of electrostatic charges also, there is going to be a certain amount of heat dissipation. So there is a need to convert this heat into electricity which can be used for a certain amount of temperature gradient. Next is with reference to heat driven micro actuators. Like we have shape memory alloys and bimetallic materials which rely on the thermal expansion for motion. So as far as the shape memory alloy or bimetallic materials are concerned, so when we try to actuate these shape memory alloys or bimetallic materials, it will have a certain amount of locomotion. So by applying a thermal expansion, we can expect a kind of a locomotion which exhibits over here. Next is with reference to temperature sensitive drug release mechanism. So there are a certain amount of configurations are there where by actuating these micro robots with the temperature, so we can have overall control over the targeted drug delivery. Ideally, it is a kind of so whenever we use a kind of a heat responsive polymers, these heat responsive polymers will have an impact in such a way that like these polymers get actuated when we try to supply a heat to it. In fact, in that aspect, we have these shape memory alloys and shape memory alloy polymers also. So these shape memory alloys or shape memory alloy polymers are highly responsive to heat, so that when a heat is applied, automatically it gets responsive. Next, we have the kind of a microfluidic heat exchangers which are efficient for cooling in biochemical assemblies. So basically, wherever there are a certain amount of biochemical assemblies are there, by supplying a heat to it, we can have a responsive system. Next, we have a thermoresponsive hydrogel's. These thermoresponsive hydrogels that change the volume with temperature variation. Now, let me just give you a small demonstration or a kind of a small insight about these shape memory alloy biomorph, which is being developed in our laboratory. So, as far as the shape memory alloy biomorphs are concerned, so we all are aware about shape memory alloys. In fact, we will be discussing about shape memory alloys. These shape memory alloys comes under the category of smart materials. Let us consider I have a spring. So, when I try to deform the spring will be turned in the form of a wire. Now, in order to bring back to its original shape, when we try to supply a heat to it, it comes back to its original shape. So, ideally, we are trying to incorporate a kind of a conduction mechanism to these kind of shape memory alloys. So, when we try to integrate a conduction mechanism, these shape memory alloy will try to contract, and then basically we call it as an actuation. So, the shape memory alloy gets actuated and it gets displaced. Now, if you closely observe the actuation of these shape memory alloy structures, so like the actuation is happening because of the heat transfer capability and the switching between the austenite and the martensite phase. So, when we have a switching between an austenite and martensite phase, so appropriately a displacement, it exhibits a kind of a displacement. It can also be used as a kind of a temperature sensor for different applications. Okay, so one of the key challenges which is involved in such kind of shape memory alloy is like a training of these structures. So this is where exactly so we had demonstrated. So we had integrated kind of a Kapton polymer so that it becomes a kind of a biomorph structure. So that one way of actuation is taken care by the shape memory alloy and the return stroke is taken care by the biomorph. If you see in this particular video, so where there is a kind of an actuation and an SMA biomorph, there is the sample is kept on it and then it actuates, and when we try to remove it, it comes back to its shape. So ideally we have a kind of a SMA biomorph, and then there are pads which are there, and these pads, when we try to give an electrical pulse to it, it gets actuated, and appropriately we can see a kind of a system. Now, if you closely observe the different process parameters like which are being which caters towards this shape memory alloy requirement or this heat transfer requirement or heating related aspects. So when we look into the scaling in thermodynamics, these thermodynamics governs the energy conversion, heat transfer and work in a system of all size. So when systems are miniaturized to a micro and nano scale, the thermodynamic property do not scale linearly, which will lead to a different behavior in energy exchange, efficiency and heat dissipation. So in that aspect, we have a thermodynamic quantity, there is an equation, and the scaling with size. So when we look into the thermodynamic quality, we have a volume in place, the surface area, the mass, the heat capacity which is represented as Cp, the work done W, the energy storage U and the entropy change. Appropriately, we have an appropriate equations which are being integrated over here, and the scaling in size is represented with reference to the different parameters. So ideally it depends upon the process how we are taking out. Now when we try to look into the specific scaling laws in a thermodynamics is concerned, the first law of thermodynamics basically it talks about the energy conservation, that is del U equals Q minus W. So the internal energy U scales with mass K3, meaning the micro robot stores less thermal energy. Work done W is PV also decreases, making energy storage and conversion challenging. These micro robots requires high energy density materials for efficient operation. Similarly, when we try to look into the second law of thermodynamics perspective point of view, we have an entropy and efficiency where ds equals del Q by T. So at micro scales, at heat exchanges which occurs more through the conduction and radiation than the convection, the entropy fluctuation increases because of the thermal energy which is limited to it. Similarly, when we try to look into the scaling of heat transfer in thermodynamics perspective point of view, where it is governed by the equation Q equals mCp del T, the heat capacity Cp, where the Kp drops, making micro robots more sensitive to temperature changes. Radiation perspective point of view, it dominates at micro scale, making the thermal coating and the emissive material crucial. Now, why thermodynamic scaling matters in micro robots? So, in the case of a thermodynamic scaling, the thermal management challenges, the heat dissipates differentially at small scales, requiring a specialized cooling strategies. So, these micro robot must use radiation and conduction based cooling instead of convection. Energy storage and efficiency perspective point of view, it has a limited volume, means it reduced energy storage capacity, and the micro heat engine are less efficient and alternative energy conversion methods are required. When we look into the actuation and motion perspective point of view, the thermal expansion actuators behaves differently at small scales. Like we had discussed about the overall design of shape memory alloys, thermoresponsive polymers which can be used for the movement. With respect to biological and biomedical micro-robotic perspective point of view, there are going to be a controlling temperature in medical and micro-robot, which is considered to be a crucial and for safe operation, and the heat transfer affects the drug release mechanism, which is considered to be a kind of a biocompatible structures. So in summary, if we try to look into these thermodynamic structures, so these thermodynamic structures are well governed by the different application as well as the different actuation perspective point of view. So when we try to look into the application perspective point of view, either with reference to energy efficiency or either with reference to the locomotion, there is going to be a certain amount of heat which is going to get generated. Sometimes it is because of the friction also, certain amount of heat needs to be generated. So that can be efficiently controlled by catering the different parameters, appropriately aligning the geometries, and appropriately having a power management to the system for effective control over the movement. Okay, so in fact this thermo-responsive system with reference to shape memory alloy perspective point of view, or with reference to these electrical thermal resistance perspective point of view, it has quite a good amount of applications in designing these micro robots with these systems. Now let us overall, if we look into the different thermal management challenges. So one of the thermal management challenges is with reference to heat dissipate, which differently at a small scale, and it requires a specialized cooling strategies. So now we will discuss about scaling in optics. So as far as optics is concerned, so like with reference to micro robotic perspective point of view, these optics is going to play a vital role, especially towards actuation. In certain cases, it is also used for a kind of a sensing related applications. For example, like if we need to study the overall locomotion of a micro robot, there such kind of optical based systems can be effectively used. So application of these optical based systems will have an impact towards towards understanding towards monitoring or understanding the behavior. So in optics, when we try to look into the scaling laws, it refers to the mathematical relationship that describes how the optical properties like beam size, focal length, or diffraction pattern changes when the physical dimensions of an optical systems are scaled up and down. Now let me just introduce you to the different parameters of these optical laws, where we have an object in place. This S is considered to be the working distance, F is considered to be the focal point. So we have an erected image and we have an inverted image in place. From the erected image, the structures are projected and it is being fed into an inverted image. So some of the key points about the scaling laws in optics is concerned. So we have a geometric scaling. The fundamental concept behind this geometric scaling is where all the length in an optical systems are scaled proportionately, allowing for designing of a similar system at different sizes. So this is one part with reference to geometric scaling. Diffraction scaling perspective point of view, as the size of an aperture decreases, the diffraction pattern spreads out proportionally, impacting the resolution of the imaging system. Next, we have the lens scaling. So in the case of a lens scaling, when scaling a lens system, the focal length and the diameter should be scaled proportionality to maintain a kind of a good image quality. So this is where exactly these lens scaling will try to have an impact. Now when we discuss about this beam propagation scaling, so if you look into a beam propagation, so we have a beam wave size and the divergence angle of a laser beam which scale with the size of the source of the aperture. So ideally, if you try to look into the conventional configuration of a beam is represented in the form of a Gaussian beam profile. So conventionally, any light, if you take, it will be in the Gaussian beam profile, where the energy is focused close to around 85%. So the 85% focus can be used for having a kind of a responsive behavior in the case of a for actuating a system. Like one good example is light driven systems. Wherever we are trying to use a light driven system, we can use this Gaussian beam profile based laser for an appropriate actuation, and even it can be used for a locomotion also. So these beam wave size and the divergence angle of these laser beam scale with the size of the source of the aperture. When we look into the fundamentals of these optical scaling laws, there are different optical parameters which are being contributing towards this fundamental optical scale. One is with reference to wavelength. These, as far as wavelength is concerned, so it is independent with reference to the scaling. Next, we have the refractive index, which is represented as n, and it has a no scaling impact. We have a Rayleigh criterion, which is represented as theta. So theta is 1.22 lambda by d, which is inverse as k power minus 1. When we have a diffraction limit, which is represented as d, so d equals lambda 2n sine theta, where it is inverse k inverse. We have a focal length f. The f is directly correlated to d, which is at k, and then we have a light intensity I, which has a direct relevance towards p by e. There is a kind of an absorption cross section, which is represented as sigma. So which is, when we try to correlate the scaling with size k, it is represented as k squared. Now, when we look into the scaling laws for a lens system, for designing a lens, scaling is trivial, at least in principle. If the focal length f, if the focal length f and the lens diameter b and other length parameters are enlarged by a factor m. So there is a parameter called lateral aberration. So these lateral aberration is denoted by this symbol, which will be enlarged in proportional to m. So here we have a travel time del t of the light scales with m. Size of the image field del x del y scales, which is represented as m squared. Volume and the weight scale, which is represented as m cube. The resolution del x due to diffraction does not change with m, since del x equals lambda f, which depends upon the wavelength lambda and on the aperture angle, which is represented by a stop number f. So in fact, I can just show you the figure. So this is a kind of a figure. So in this figure, we can have a representation over the f and the lambda. So where we have a kind of a lens system, and through this lens system, so we can have a control over the aberration, and then and the overall f is the which gives a kind of a stop number. So the wave aberration is represented by w, which describes the deviation of the actual wavefront from a perfect spherical wavefront, and the scale with it represented as m. The wavelength lambda, which is always remains a kind of an unchained. So this is a kind of a scaling behavior in the case of a lens system, where the different parameters are being addressed. Here the lateral aberration varies the scale change. The curvature angles and the diffraction blur remains the constant. Now, why there is a need to go for an optical scaling matters in the case of a micro-robotic system? So in the case of a miniaturized optical sensor, these micro-robots rely on the optical sensor for navigation, obstacle detection, and biochemical sensing. When we look into the optical communication in micro-robotics perspective point of view, like when there are two robots or two micro-robots are there, or when there is a span of micro-robots are there, there is a need to have a kind of a communication. So these optical signals are used for data transmission, wireless power transfer, and swarm coordination. At small scales, higher frequencies, UV, visible and UV are preferred for compact optical devices. So these are some of the key applications where optical communications in micro robots can be deployed. Optical actuation for micro robotics perspective point of view. The light can be used to move or deform micro robots using optical tweezers or photothermal actuation. So at small scales, optical force become dominant over the mechanical forces. Next, with reference to diffraction and limited image in micro-robotic perspective point of view, these miniaturized imaging system suffers from a diffraction limitations, and these micro-robots highly require a kind of a higher resolution imaging for a precise operation. So this is considered to be one of the key requirement for considering this diffracted limited imaging. Now, when we try to look into the application of these optical scaling and micro-robotic perspective point of view, these optical scalings are effectively used in endoscopic micro-robot, especially in the case of non-invasive surgery. Infrared based optical communication for micro-robotics as discussed earlier. So for a kind of a interaction between two micro-robots, or if we need to govern a span of micro-robots appropriately, we can be deployed. We have there is an optical tweezers for manipulation where there is a cell and a nanoparticle which is being kept over here. Photothermal actuation for soft micro-robot movement is considered to be one of the key aspects with reference to the system. We have a plasmonic heating for microfluidic propulsion. So as far as these plasmonic heatings are concerned, so it is deployed for appropriate light trapping related activity. We have a micro lidar system for mapping small scale environments. A laser driven micro robot which is used in the kind of optical and rectanas. So like you might have seen a kind of a cockroach where it has a kind of a rectanas. So for those things, such kind of these laser driven based systems are deployed. In fact, when we discuss these biomimicking based micro robots, we will be discussing about these concepts. Now we will discuss about the influence of quantum effect in a micro robotic system. So as far as in the case of a quantum effect, first we need to have some understanding about the different parameters which are being catering towards the quantum effect. One of the parameters includes the quantum tunneling. It's a quantum mechanical phenomenon that occurs when a particle passes through a barrier that would normally be impossible to pass through it. It is also known as a barrier penetration. Then we have a kind of a Casimir effect. The Casimir effect is a quantum force that causes attraction between two uncharged conducting plates held very close together. Next, we have a kind of a quantum entanglement. The quantum entanglement is a process whereby energetically degenerate states cannot be separated, and electron or photon in these states are essentially indistinguishable. Next, we have the kind of a wave particle duality. It is an idea that matters and light can exhibit properties of both waves and particles depending on how they are observed. This concept is a fundamental principle of quantum mechanics. Next, we have a superposition. The superposition in quantum mechanics, the superposition refers to the ability of the quantum particles to exist in multiple states simultaneously, meaning it can be in a combination of different possible states as and when it is measured. So as far as these quantum effect so the influence of these quantum effect in micro robotics is concerned, these quantum effect in micro robots refers to the phenomenon where the behavior of the micro robot is significantly influenced by a quantum mechanical principle, such as quantum tunneling or superposition due to its extremely small size. It leads to a unique capabilities which not possible with larger robots, particularly in areas like precise manipulation. Like we will be discussing about AFM as a micro robot. So where these quantum has an impact, especially with reference to precise manipulation, sensing at a micro scale level. In certain cases, if we need to have a kind of a micro manipulation, such kind of quantum effect will have a potential impact towards micro manipulation. So unlike classical physics, these quantum phenomena such as tunneling, superposition, and entanglement play a crucial role in sensing, energy transfer, actuation, and communication in micro-robotic related system. Now, let us discuss some of the different quantum effects, how these quantum effects will have a kind of a impact in the micro-robotic related applications. One of the quantum effect is called as a quantum tunneling, where we have a nanoscale sensor and actuator. It enables a nanoscale actuator and a quantum diode and an ultra sensitive sensor which is being impacted. Next, we have the Casimir effect. It's a kind of a surface adhesion and energy harvesting. It has a control over the micro-robot interaction with the surfaces. We have the quantum entanglement, which secure a communication and a computing, and enhance micro-robot coordination and a cryptography. Is one of the key impact with reference to micro-robot perspective point of view. One important quantum effect is called as a superposition. It has a quantum sensing and a computing. It enables a quantum-based sensing and a computing of a micro-robotic system. As far as the quantum effect is concerned, we have a wave-particle duality. It has a photonic micro-robot and an imaging. It is used in nanoscale imaging and a photonic propulsion system. When we look into the application of these quantum effects in micro-robots, this quantum tunneling for micro-robot, which is effectively used in micro-robotic actuation and sensing. These quantum tunneling, they enables a nano actuator that bypass the classical motion constraint. As far as application perspective point of view, it is used in a nanoscale MEMS switches for micro-robot control, tunneling junction based energy harvesting for self-powered micro-robots, a quantum tunneling sensor for detecting single molecule in biological environment. Similarly, when we have a Casimir effect for surface adhesion and energy harvesting, these quantum vacuum fluctuation creates Casimir forces that affects micro-robots which moves near to the surface. Application perspective point of view, these electrostatic adhesion for wall climbing micro-robot and a Casimir energy harvesters for power generation in nanorobot. Similarly, we have a quantum computing for SWAN micro-robot coordination. This quantum algorithm, it optimizes a micro-robot SWAN for efficient task execution. So there are different applications are there. One of the applications include the quantum inspired optimization for micro-robot navigation in complex environments, quantum neural network for real-time micro-robots and decision makings, quantum enhanced cryptography for secure data transfer in micro-robot networks. Quantum sensor for extreme sensitive in micro-robot is concerned. We have a quantum sensor, leverage entanglement and superposition for ultra precise measurements. With reference to application perspective point of view, we have an atomic scale accelerometers for micro-robot stability control, a quantum magnetometers for precise magnetic field sensing. Now, let us discuss about the different challenges which are being evolved with reference to the scaling quantum effect. So, as far as these scaling quantum effects are concerned, the scaling quantum effect, it has a potential with reference to real world micro-robot, especially in complex environment. It maintains a quantum coherence in biological environment is in challenging cases. And the quantum computing for micro-robot is in an early stage, but it has a great potential. In fact, this is considered to be one of the key areas where there are more focus are currently being evolved with reference to usage of these micro-robots for micro manipulation as well as a micro sensing perspective point of view. Some of the solutions with reference to these challenges are like hybrid classical quantum micro-robots may integrate a quantum sensor while operating with classical mechanics. Second, advance in nanofabrication will have a better control on this Casimir forces and these quantum tunneling as well as these photonic interactions. So, to give you an overview of this particular module, so we had discussed about the different scaling laws which are being deployed. So we had discussed about the how these structures on a geometric perspective point of view, how on a macro it behaves and how on a micro level it behaves. So we also had some discussion about these rigid body systems. We also had some discussion about electrostatic, the influence of electrostatic structures, electromagnetic structures, electrical structures, fluid structures, thermal based systems, and then we also had a discussion about this optical based systems, scaling laws in optical based systems, and finally we had some discussion about the quantum effect. So we will be discussing about the other aspect of these micro robotic systems in the upcoming classes. So this module gives you a fundamental about the overall parameters, fundamentals and design considerations which we may need to consider when we are approaching a micro robotic systems.